m of f1 is less than or equal to m of f2. We have this for open sets. If G1 is a subset of G2 and both G1 and G2 are open sets, then m of G1 was less than or equal to the m of G2. Now we're going to prove this for closed bounded subsets. Okay, let us have a look to the previous theorem. We want to use it here. Lemma 2.3 says that if I equals to the open interval from A to B containing a closed set F, then m of F equals to m of I minus m of I except F. Okay, now we want to use it to prove lemma 2.4. Let I be the open interval from A to B, and suppose that F1 is a subset of F2 as the hypothesis, and F2 is a subset of I because they are bounded. Let me add 2.2, we have m of I minus f2 is less than or equal to m of I minus f1 because this one is open. F1 is a subset of F2. Now F2 complement is subset of F1 complement. Okay, what is F2 complement? F2 complement is I minus F2. It's a subset of I minus F1, and both of them are open sets. Okay, open. Now by the monotonicity of the measures of on the open sets, we have m of I except f2 is less than or equal to m of I except f1. That is, m of I minus m of f2 is less than or equal to m of I minus m of f1. You can omit m of I from both sides of the inequality, and finally you have m of f1 is less than or equal to m of f2. Lemma 2.5 says let F be a closed subset of a bounded set G. Bounded open. Okay, now we're gonna go ahead to prove that M is monotone, not only on open and closed set, but of course on any two sets. Monotone. If F is closed and G is open and F is a subset of G, then M of F is less than or equal to M of G. It's not hard to see if I equals to A to B be an open interval containing G, then I equals to G union with I except F. Where the set G and I minus F are open. Open and open. Okay? By theorem 2.4, M of I is less than or equal to M of G plus M of I minus F except F. Now, M of I is B minus A is less than M of G plus, and M of I minus F is B minus A minus M of F. And finally, we are done. Okay? Move it to the other side. We have M of F is less than or equal to M of G. Now, if G is an open subset of a bounded closed set, okay, the reverse. If G is a subset of F, then M of G is less than or equal to M of F. You need to take A to be the infimum of F and B to be the supremum of F. The sets G and AB minus F are open and disjoint. It's clear that G union with the A to B minus F is a subset of A to B, and therefore by the previous theorems and lemma 2.2 we are done. Nothing to prove. M of G is plus M of A minus B, A to B minus F, this one is less than or equal to the length of this open interval. It is B minus A, and this one is A minus B minus M of F, and you are done easily. Let Q and V be bounded sets of real numbers such that each of these two sets is either open or closed. U and V are bounded sets of real numbers, okay, such that each of these two sets is either open or closed. U and V maybe are open and maybe are closed. We have, if U is a subset of V, then M of U is less than or equal to M of V. From theorem 2.2, we have the measure of a bounded open set G is the greatest lower bound of measures of bounded open sets containing G. Okay? M of G is the infimum of M of G prime such that G prime is a superset of G and G prime is open and bounded. Theorem 2.2 says that if an open set G1 is a subset of a bounded open set G2, then M of G1 is less than or equal to M of G2. In words, measure is a monotone function on the set of bounded open subset of real numbers. Okay, now we have M of G is the infimum of the sets of measures of G prime such that G prime is a superset of G and G prime is open and bounded. We can establish a similar result for the closed sets. We want to prove two measures, in an outer measure and an inner measure. Okay, let G be a bounded open set. Then M of G is the supremum of M of F such that F is a subset of G and F is closed. Okay, for bounded open sets, we have this one. M of G is the supremum of M of every, the measure of every closed set contained in G. Trivially, F is bounded because G is bounded. Okay. Now compare these two statements. M of G is the infimum of M of G prime. M of G is the infimum of M of G prime, such that, let me take it to the next page and you can compare this. Look at this M of G. M of G is the infimum of M of G prime such that G prime is a superset of G and open and bound. Now, M of G is the supremum of M of F such that F is a subset of G and F is closed. We can prove it by theorem 2.5. Let me see what is theorem 2.5. Says that if U and V are bounded sets of real numbers such that each of these two sets are either open and closed, then if U is a subset of V, then the measure of U is less than or equal to the measure of V. Now, we have the measure of F is less than or equal to the measure of G here for any closed subset F of the set G. According to the approximation property of supremum, you know, the definition of supremum, we need to show that for a given positive epsilon, there is a closed set F subset of G such that M of F is greater than M of G minus epsilon, because M of G is the supremum of these sets. Okay, so M of G minus epsilon M of G minus epsilon is not the supremum, is not supremum. So there is an F subset of G such that M of F is greater than M of G minus epsilon. Okay? Let me add Ahmad Ali. Welcome, Ahmad. G has its own component intervals, a family, at most countable family of its component intervals. We can write G to be the union of open intervals AI to BI, such that A belongs to J, and J is finite or countable. And the measure of G is the sum of the lengths of these intervals. Measure of G is the sum of measures of any open intervals, which is the one of its component intervals, and the measure of an interval is its length, of course. So M of G equals to sigma BI minus AI. Again, of G is the sum of the lengths of its component intervals. Therefore, there is a finite set J0 subset of J such that this sum on the index set J0 BI minus AI, where I belongs to J0, is greater than M of G minus half epsilon. Now, let N be the cardinality of J0. Okay? For every I in J0, we choose an interval and a closed interval, like AI prime to BI prime, so that AI prime to BI prime is a subset of this open interval, and BI prime minus AI prime is greater than BI minus AI minus epsilon over 2 times n. You can prove this by exercise 2.7. Okay, you can do it as homework. And define a closed set F by this F is the union of this closed interval. Note that F is closed. Why F is closed? Because these are closed intervals, and every closed interval is a closed set, and J0 is finite. Okay, any finite union of closed sets is closed. Okay, now M of F equals to sigma, or the sum of bi prime minus ai prime, because this is F, and it is greater than sigma bi minus ai, I belongs to J0 minus half epsilon, and it is greater than M of G minus epsilon, and because epsilon is arbitrary, now this is the desired result. Now, we have another theorem. 2.7 says F is a bounded closed set. Then, this is the dual definition for the measure for the open sets. If M is bounded and closed, then M of F is the infimum of M of G, such that F is a subset of G, and G is open and bounded. Okay? If I is the open interval containing the set F, because F is bounded. F is bounded, so such an open interval exists. Then I minus F is open and bounded. By theorem 2.6, for a given, the previous theorem, for a given positive epsilon, there is a closed set F0 being a subset of I except F, such that M of F0 is greater than M of I except F minus epsilon, and this is equal to B minus A. This one is B minus A minus M of F, because F is a subset of A to B. M of I minus F, this is I. This is the open interval I. M of I minus F is B minus A minus M of F. Okay? And we have minus epsilon here. Now, the set G0. G0 equals to I minus F0 is open, of course. Because F0 is closed, I minus F0, I except F0 is open and contains the set F. Okay, contains the set F. Therefore, by the above inequality, M of G0 is equal to M of I minus F0 equals to B minus A minus M of F0, and it is less than B minus A minus B minus F A plus M of F plus epsilon, because M of F0 was less than B minus A minus M of F minus epsilon. So this B minus A minus B minus A is omitted, and we have M of G0 is less than M of F plus epsilon. Now epsilon is arbitrary, so we have M of G0 is greater than or equal to m of f. Now the result follows from the approximation property of the infimum. Now, if f is a bounded closed set, then m of f will be the supremum of m of f prime, such that f prime is a subset of f and f prime is closed. As we have this one for the case of open sets. Let me have another student. We use these results in the following theorem, which justifies definitions of the inner and outer measure in section 2.3. Let U be bounded open or closed sets. Just bounded open or bounded closed. Then M of U is the infimum of M of G, such that G is a superset of U and open and bounded, and it is equal to supremum of M of F, such that F is a subset of U and F is closed. Okay, F is closed. F, because U is bounded, so is F. Now, this is a very important theorem for any bounded open or closed sets. We have this definition, exactly definition for the measure of the set U. Theorem 2.10 says that if the set of F1 to Fn is a finite collection of pairwise disjoint bounded closed sets, and F is their union of Fi from 1 to n, then M of F is the sum of M of I count from 1 to n. Okay, the proof is not hard, and I leave it to you. Now, the inner and the outer measure. We are going to the final definition of the measure of an arbitrary set. Okay, let E be a bounded set, just bounded, not necessarily open and necessarily closed. Okay, the outer measure M of star of E, M of star of E is the greatest lower bound of measures, or the infimum, okay, the infimum of measures of all bounded open set G containing the set E, So M of E equals to the infimum of this set, infimum of M of G, such that G is a superset of E and G is open and bound. And the inner measure of E, M down star of E, is the least outer bound, the supremum. Okay, the supremum of measures of closed sets contained in the set. So M down star of E is the supremum of M of F, such that F is a subset of E and F is closed. Yeah, of course, F is bounded. Okay, it is not mentioned like the infimum case bounded. It is not mentioned because E is bounded, so is F. Now, look at this definition again, and you need to remember it in the next pages. Okay, up star and down star of E, the outer measure, the inner measure. You have a set E here. E is here. E is a subset of some open sets G, for example, GT, okay? G. The infimum of this open, the infimum of the measure of these open sets will be the outer measure of P. And something like this, outer measure of P. And dually, E contains some closed sets, okay? F. And the supremum of this, the measure of these closed sets is the inner measure of it, okay? The supremum of the measures of closed sets which contained in E will be the inner measure. Someone else? Maybe. Can you see the screen? No problem?
Yes.
زینب متوجه. outer measure, inner measure. اندازه بیرونی همون بالایی یعنی چی؟ یعنی تو یه مجموعه مثل ای داری. خب یه مجموعه مثل ای که کراندار هست. چی میگفتید کراندار رو به عربی؟ مقیده. خب این مقید هست. خب این ای بالاخره زیر مجموعه یه سری مجموعه های باز هست، مفتوحه هست، درسته؟
بله.
اون مجموعه های مفتوحه هر کدام یه اندازه دارن، یه میجر دارن، درسته؟ همه اونا رو میریزیم توی یه مجموعه. به هر حال زیر مجموعه کل اعداد حقیقی هست دیگه، یعنی توهی نیست. اون مجموعه‌ای که دارم میگم توهی نیست. شما یه مجموعه در نظر بگیر از جی هایی که مجموعه جی هایی که جی باز باشه و شامل این مجموعه مفروض ما باشه. اینو در نظر بگیر. هر کدام از اینا مثلا اسمش یه همچین جی.
لا تساوي.
این توهی نیست. چرا توهی نیست؟ چون حداقل مجموعه اعداد حقیقی رو داره دیگه که شامل همه هست دیگه، شامل ای هم. حالا این جی هایی که اینجا هستن هر کدام یه اندازه‌ای دارن. هر کدام یه میجری دارن. اونا رو همه رو بریزیم توی مجموعه و کوچکترین اونها رو در نظر بگیریم، یعنی اینفیموم اونا رو در نظر بگیریم. به این میگن اندازه بیرونی مجموعه ای. به همین صورت یه سری اف هایی هستن، مثلا فرض کنید من اسم اینو بذارم اف رو بگیرم، اف هایی که اف زیر مجموعه ای هست. خب اینم توهی نیست. چرا؟ چون حداقل مجموعه توهی رو داره دیگه. اینها هم همشون یه اندازه‌ای دارن دیگه. این مجموعه بسته ها همشون یه اندازه‌ای دارن. سوپریموم اینها رو بهش میگیم اندازه درونی این مجموعه ای. حالا در ادامه میدونید چی میخوام بگم؟ میخوام بگم که اندازه ای چی هست؟ خب دیگه بدون هیچ ستاره‌ای در پایین یا بالا اندازه واقعی چی؟ میگیم اگر اندازه بالاییش و اندازه پایینی یا اندازه بیرونی و درونی با هم برابر شدن بهش میگیم اندازه ای. اوکی؟
اوکی.
حالا گفتم اگه خواستی برای بچه‌ها توضیح بدی مفصل‌تر بگو.
يا لحظة. يقول عندنا مجموعة E هي أصغر مجموعة بمن بالأعداد الحقيقية اللي تكون غير خالية من مجموعة هي مجموعة غير خالية من هي مجموعة E. نفرض بأن هي subset من مجموعة مثلا G1 G2 G ستار، هاي اللي مخلينا إياهن. زين، يقول هاي محتوى الإي محتوى بي من جي، يعني اكو مجموعة احتمال اكبر من عندها، واحتمال اكو مجموعة بعد اكبر من عندها اللي هي G1 G2 G3، بحيث كل واحد الإي إلى قياس المجر الام، والجي هماتين إلهن قياس، والجي 2 هم إلى قياس، كلهن إلهن قياسات خاصة. فيقول لك بما ان الاي اصغر واحد راح يكون الداخلي الاي داخل جي 1 والجي 1 داخل جي 2، الاستار مخلينا اياها وين لي فوق، بما انه قايل لك اياها داخليه راح نكون عندنا انفيموم قياس للجي، اصغر قياس هي الاي، ومن يخلي لنا ستار لي جوا راح تكون شنو هو سوبريموم، يعني من هو الاكبر راح ناخذ ان الجي 2 اكبر من محتواه بي من الجي 1 والاي مجموعه الاي، يعني كل اللي يحكي عن قياس المجاميع المحتوى الاي محتوى بالجي 1 والمحتوى في جي 2، والقياس مالتهم راح يكون عندنا بما ان الداخلي راح يكون اصغر، وبما ان عندنا قياس الجي 1 بالنص وعندنا قياس الجي 2 اكبر واحد، راح يكون عندنا اكبر قياس اللي هي سوبريموم المن للجي 2. وضحت الفكره؟
اوکی ممنون زینب.
ممنون.
میگم این ادنا که میگی منظور همون اندنا هست؟
ادنا یعنی داریم.
ادنا یعنی داریم.
داریم.
بعد شنو هم میگی؟
شنو یعنی چی؟
یعنی چی؟
چی؟
بعد به من انشالله عربی یاد بدی.
انشالله.
It is clear that the outer measure of any set E is greater than or equal to 0 and is less than infinity, because we suppose E to be bounded, and we have this for the inner measure too. Now, by theorem 2.9, we have the, what is the theorem 2.9? Okay, this one. That is, if U is a bounded open or closed, okay, then M of U equals to the infimum of M of G. G is open, and supremum of M of G. M of F. F is subset of U. Now, if we have this for closed and for open sets. If G is open, by theorem 2.9, we have M, the outer measure, is equal to the inner measure. So we call it the measure of G. And of course, for closed sets like F, the outer measure is equal to the inner measure by theorem 2.9, and we call it the measure of F. So we define the measure of any set F which is closed and any set G which is open. We are going to define the measure of any set, not necessarily open and closed. For every bounded set E, we have this theorem for any bounded set E, and the inner measure is less than or equal to the outer measure. It is straightforward because of the definition of supremomes and infimomes, and some statements by theorem 2.5, for example, and you can see the proof here. then monotonicity property of inner and outer measures is established in the next theorem. If U and V are bounded sets, okay, then U being a subset of V implies that the inner measure of U is less than or equal to the inner measure of V, and of course the outer measure of U is less than or equal to the outer measure of V. Is not hard to see, straightforward. Now we obtain, this is theorem 2.12, we obtain a generalization of theorem 2.4 as the result of the following theorem. Countable subadditivity of the outer measure. Let's have a look to theorem 2.4. Theorem 2.4 says if a bounded open set G, bounded and open, okay, is the union of a finite or countable family of open sets Gi, not necessarily disjoint, okay, not necessarily disjoint, then the measure of G is less than or equal to the sum of the measure of Gi, where I belongs to the index set J. Okay, we want to generalize this for outer and inner measure. If a bounded set E, bounded, not necessarily open and closed, is the union of a finite or countable family of sets EI, and EIs are not necessarily open and closed. Okay, so E is the union of EI, and EIs are not necessarily mutually disjoint. Then the outer measure of E is less than or equal to the outer measure of EI, the sum of outer measures of EI. Look at the index set J. J is not necessarily countable. J could be a set of all real numbers, okay? First, for the proof, first we consider the case when J is countable. The result is trivial. If M star of EI, the sum of M star of EI is infinity, okay? So E is less than or equal to infinity, of course. So we assume the family M star EI, I belongs to J, is bounded or is summable. Okay, it's summable. Let positive epsilon given and F is a function from J to N be a bijection. By the definition of the outer measure, for each I belongs to J, there is an open set Gi superset of EI such that M of Gi is less than M of M star of EI plus epsilon over 2 raised to the power of F of I, because M star of EI is the infimum, is the supremum of some sets, okay? And by the approximation property of the supremum, of the infimum, infimum of measures of Gi, okay, Gi, where Gi is a subset of EI. Okay, we have this by the definition of the outer measure. Now, by the approximation property of the infimum or supremum, okay, they are similar to each other. If we have an epsilon, like epsilon over 2 to the f of I, then m star of EI plus epsilon over 2 to the power of f of I is not the infimum. Okay, is not infimum. So by definition, there exists a GI here. There exists GI such that m of GI is less than m star of EI plus epsilon over 2 to the f of I. Now, let E, it's the explanation for this inequality, okay? This inequality. Let A to be an open interval containing set E, because E is bounded, then the set A to B intersection with the union of GI, where I belongs to J, is equal to the union of AB intersect with GI, where G belongs to J, is open, because an arbitrary union of open sets is open, and of course contains E. Therefore, by theorem 2.12 and 2.4 and 2.2, we have M outer measure of E is less than or equal to the measure of this union, and its E is less than or equal to the sum of the measures of these intervals, these sets, and it is less than or equal to the measure of GI, because A to B intersect with GI is the subset of GI. Okay, so by the monotonicity of the measure M, we have this to be less than or equal to the sum of the measures of GI, and it is less than or equal to the sum of the measures and the outer measures of EI plus epsilon over 2 to the power of I, as mentioned here. I mentioned it here. Okay. Now it's the geometric series. Okay, geometric series is, and the sigma, it will be epsilon, and it's equals to the sum of the outer measures of EI plus epsilon. Now, M star of E is less than or equal to the sum of M star of EI plus epsilon, and so epsilon is an arbitrary positive number, so we have this inequality as desired. The case when J is a finite set is reduced to the previous one by adding countably many empty sets to the family EI. Oh, okay. Let me check it. J is countable, finite or countable. I said that among my boards, I said that J could be an uncountable index set. So I correct this, I correct my board. J is finite or countable. we have just proved this for countable case, and for the finite case, it is very easy because you can take many of these sets to be the empty set from somewhere to the infinity. Okay. If J is a finite set, it's reduced to the previous one by adding countably many empty sets to the family EI belongs to J. Now, if a bounded set E is the union of a finite or countable family of pairwise disjoint sets EI, so we have E is the union of EI, I belongs to J, and EI intersects with EJ is the empty for any non-equal I and J. Then the inner measure of E is greater than or equal to the sum of the inner measures of EI. In theorem 2.13, we have E is the union of EI, okay? And we didn't suppose that EIs are disjoint, okay? We didn't suppose that EIs are disjoint, but here for the inner measure, we have to do this assumption. Okay, E is the union of EI and EIs are disjoint. Then the inner measure of E is greater than or equal to the inner measure of the sum of inner measures of EI. Okay, the proof is similar to the proof of the previous theorem. It's sufficient to consider the case where J is countable, and for the finite case, we can do so as we did in the previous theorem. I think I can leave it to you. It's no important proof. And note that unlike the case of the outer measure, the claim of the previous theorem fails to hold if the sets EIs are not pairwise disjoint. Here is an example. Let E1 equals to the closed interval from 0 to 1 and E2 be the closed interval from 0 to 2. Then the inner measure of E1 union with E2 is equals to 2 because E1 union with E2 is E2, okay? Because E1 is a subset of E2. So M of E1 union with E2 is M of E2, M of this closed interval, and it is equals to 2. But the inner measure of E1 is 1, the inner measure of E2 is 2, so 2 is less than 3 if the previous theorem is right for the case for the non-disjoint sets. So we have to suppose that EIs are pairwise disjoint. Now we have the last theorem of this section. It's very important property of inner and outer measure, and we use it several times in the rest of this chapter. Theorem 2.15, let E be a bounded set and I is the open interval containing E. Okay? E is a subset of the open interval from A to B, then the outer measure of E plus the inner measure of I minus E equals to M of I equals to A minus B. Okay? For the proof, see by the definition of the outer measure for a given positive epsilon, there is an open set G0 containing E such that M of G0 is less than M star of E plus E, because the outer measure is infimum. Okay, so M star of E plus E is not the infimum. It is not the infimum. So there is an open set G0 such that the measure of G0 is less than to the measure of the outer measure of E plus epsilon. Someone else? Adnan? Welcome, Adnan. Will be a subinterval of A to B such that A prime minus A is between 0 and epsilon, and B prime minus B is between 0 and epsilon. We have here A, B, A prime, B prime, here is A prime, A plus epsilon, and here is B minus epsilon. Okay, so let G be the union of these intervals and sets I intersection with G0, union with the interval A to A prime here, and B prime to B, and I intersection with G0. Then we have M of G is less than or equal to the sum of measures of these intervals, and this is M of G0 plus A prime minus I plus B prime minus B minus B prime, and it is less than epsilon, less than epsilon, less than M star of E plus epsilon. So it is M of G is less than M star of E plus 3 epsilon. They said F equals to I minus G is closed. It's closed because G is open. F is A prime, B prime intersection with G complement. You can prove it in exercise 1.40. Since E is a subset of G, we have F equals to I minus G is a subset of I minus E, because E is a subset of G. Okay, E is a subset of G. Hence, the inner measure of I minus E is greater than or equal to the measure of f. The measure of f is equal to the measure of I minus the measure of g, and it is greater than the measure of I minus this one. Because of this inequality here, we prove that m of g is less than m, the outer measure of e plus 3 epsilon. Now, because epsilon is arbitrarily positive, we have the inequality m, the outer measure of e plus the inner measure of I minus e is greater than or equal to the measure of the interval I. Now, in order to obtain the reverse inequality, we want to prove this one. Okay, we have the outer measure of E plus the inner measure of I minus E is less than or equal to, we want to prove this one. Okay, let us select a closed set F such that F is a subset of I minus E. Okay, and M of F, the measure of F, is greater than the inner measure of I minus E minus epsilon. It's by the approximation property, because the inner measure is a supremum. Inner measure is supremum. So the inner measure minus an epsilon is not supremum. So there exists F, a subset of I minus E, such that the measure of F is greater than the inner measure of I minus E minus epsilon. The set G equals to I minus F is bounded open, because I is closed, I minus F is open, F is closed. Okay, F is closed, yes, F is closed. I minus F is F complement. It's bounded open sets containing the set E. Therefore, the outer measure of E is less than or equal to the outer measure of G, and it is equal to the measure of I minus the measure of F. The measure of I minus the measure of F, and the measure of F, the measure of F plus epsilon is greater than the measure of I minus E. Measure of I minus E, so we have this inequality, and epsilon is arbitrary, so we are done, and this yields the desired inequality. زینب میخواید یه ربع ساعت استراحت کنیم، بعد بیاین قسمت بعدی رو بگیم.